All right, so let's do a practical filter design example. This is really practical stuff here. This is definitely something that you could see on an exam. This is something you could see in a project, really, and I think it's really practical. So let's go ahead and do it. So I wrote some instructions here. It says a meeting audio, so some kind of a meeting, a voice meeting, was recorded and needs to be reanalyzed. The audio speech or the speech audio was between 90 hertz and 255 hertz. So that's the typical range for adult speech, is in this range of 90 hertz to 255 hertz. And there's a really high frequency obnoxious noise in the recording at 7.2 kilohertz. So really high pitched, like a dog whistle kind of a sound that we definitely don't want to hear when we reanalyze this speech. And so how can we get rid of this? Well, the example that I wrote here says design a filter to attenuate the noise, which is this part of the signal, to at least 1/10 of the original magnitude. So we basically want to attenuate this noise by a factor of 1/10, and we want to leave the speech basically untouched. Okay? So how would we go about doing that? Well, the way that I think that it makes the most sense to design the filter would be to start with the frequency response that we desire. So let's go ahead and put frequency here. We'll obviously put our magnitude here. We can just call it magnitude of our, I'll just call it magnitude of H, some transfer function, our audio signal. Doesn't necessarily need to be voltage. I guess we can call it V out over V in. Doesn't really make a difference. Okay, so what we want is, let's just put 7.2 kilohertz right here. We can put something like 72 kilohertz here. We can go down a decade and put 720 hertz. Down another decade and put 72 hertz. And yeah, that looks pretty good. And so where is the range of the speech that we're interested in? It's at 90 to 255 hertz. So that would be like maybe right in this range. That's the speech that we're interested in. Is it in between these frequencies? This might be 90 and this might be 255. Okay. And then the bad noise that we're trying to get rid of is right here at 7.2 kilohertz. And so we want to attenuate by 1/10, right? Well, what is my magnitude in dBs if I'm trying to attenuate by 1/10? So that would mean that I would want the magnitude of V out over V in to be equal to 1/10. And so 20 log of 1/10, which that's going to be how we get it into dBs. If I put that in my calculator, I'm going to get negative 20 dB. So I basically am saying that I want the value of my frequency response to be negative 20 dBs or lower at 7.2 kilohertz. And that obviously means that it would be negative 40 at 72 kilohertz if I design my filter with a 20 dB per decade drop off like we've seen simple filters give us. And that would mean that at 720 hertz, I would be up at 0 dB, which basically means I would be passing that signal with no attenuation whatsoever. And so this would give us exactly what we need, right? This would give us this kind of response right here, where of course in reality this is minus 20 dB per decade, right? And this would actually start to drop. Of course, it's not going to be exactly 0 dB at the cutoff frequency. It would be, what would it be? Hopefully everybody knows it would be minus 3 dB, which we saw previously. That would be right around here. But okay, so we're basically done with what the frequency response should look like, but now how do we actually design the filter? So to design the filter, we now know that we need a cutoff frequency of 720 hertz. So FC needs to be 720 hertz. Okay? And we know there's an equation for FC. It's 1 over 2 pi RC. So now all we have to do to design the filter is plug this 720 hertz in right here, solve for R and C, and pick some values, and we will have designed our filter. Okay, so let's go ahead and do that real quick. Let's go over to the next page. I'll just take this with us. Okay, so we're going to say 720 hertz is equal to 1 over 2 pi RC. And we're going to say RC is equal to 1 over 2 pi times 720, which is 1 over 1440 pi. Okay, and let's just pick one of our two values here. Let's just let R equal 1 kilo ohm. Okay, so now we have our R and we can just solve for C. That's basically what we're going to do in most design problems. Is we're going to be left to choose something. So let's just choose our R to be 1 kilo ohm. And that means that we can just divide by 1K. And we can say C is equal to 1 over 1440 pi times 1K. And let me throw that into my calculator. 1440 times pi times 1,000. And I'm going to get 221 nanofarads for my capacitor, which is a totally reasonable value. And I'm done. I've designed my filter that's going to attenuate my signal, my noise, and pass through my speech. So this would be my filter. I would send my messy audio signal in here, right? And this is going to include the noise. And then what we're going to get out is going to be clean audio. And that is with R equals 1 kilo ohm, and my C is 221 nanofarads. Okay, so that's our filter design example 1. Hopefully that makes sense to everybody. Let me just write my values again and just box them. All right, so that wraps up this example. In the next video, I'm going to do another filter design example, and we're getting really close to finishing up this module, so let's just keep trucking along. We're almost there.